And then we had our Bronsted Lowry definition of an acid and a base. And who remembers what the two different definitions were? Yeah, for Bronsted Lowry acid, right? That is a proton donor. And what was the base then for a Bronsted Lowry base? Yep, this was a proton acceptor, right? And because of the nature of one being a donor and one being an acceptor, it means that after something donates a proton, it is now available to accept a proton, right? And so it gives this idea of conjugate pairs, where once you have your acid donate its proton, since it can now accept a pair, it's called a conjugate base, right? So this gave the idea of conjugate pairs. And this is especially true, and I'm going to put in parentheses here, for weak acids and bases. Sorry, the pencils. Pencil's glitching out right now. See chemical reactions. It's just the interface. All right, so that gives us the idea of conjugate pairs. And the conjugate pairs, again, where once we donate a proton, you're then available to accept a proton, right? So now you can act as a Bronsted-Lowry base, right? Because you're available to accept a proton. And so for these, once this load, for these conjugate pairs, you can have both conjugate bases and conjugate acids. And that just depends on what you were originally or how you write the equation, right? So we also introduced this idea of equilibrium, right, where we have the fishhook arrows. So instead of just reactions moving in one direction, they can go back and forth, right? And the reactions are always moving back and forth, but once we reach equilibrium, that's at the point where the concentrations of the reactants and the products are no longer changing. All right. I'm going to restart this. How does it? Oh, so it's none of the. That said 100%. Okay. All right. Well, I'm just gonna start writing on this on the chalkboard. All right. So once you have. Right? Let's say this is our arbitrary weak acid, right? We add it to water, and what it does is it donates a proton to the water, it donates a hydrogen. We write these fishhook arrows that represent an equilibrium. To then generate our conjugate base and our hydronium. Right, our hydronium, if you're thinking about an Arrhenius definition of an acid and base, what is the Arrhenius definition of an acid or a base? Does anyone remember? Yeah, this is what defines it being an acid. Does it make H3O plus in solution? And this is what defines it being a base. Does it make hydroxide in solution, right? So those, in terms of the Arrhenius definition, are what defines an acid or a base. Really, this is how we're going to define acidity or basicity of solutions. This is concentration of those two species. But the generic form, we can write our conjugate pairs like this. This isn't arbitrary, right? We just use A to represent any acid. We did some practice last time. For example, if we looked at acetic acid, it was H3C2O2H. OH plus water, right? This would represent the actual acid that we're looking at. And after it goes through a reaction with water, it donates a proton and it becomes H3C2O minus, and then it generates our hydronium in water, right? So HA just represents whatever it is that donates the proton, right? So that would be this whole part would just be like A. And this is called our acid because it is a proton donor. This is then called the conjugate what? This would be the conjugate base, right? Our acid donates a proton to then become a conjugate base. In the opposite direction, now we have A minus, right? If we write this reaction the other way, except we're reacting with water on the reactant side, this would be our base because it's accepting a proton, right? This would be our conjugate what then? This would be our conjugate acid in this case. And it makes hydroxide, which is what we define as intermediate base. All right, so this is where we left off last time, looking at conjugate pairs. And can we identify or not identify the conjugate pairs? Okay, it's writing now. Thank God. All right, so that's where we left off. And so we had some examples. We were asked, here we looked at chlorine, what's the conjugate acid, what's the conjugate base? It's important to be able to identify the conjugate pairs for each of these different systems. And so if you were to be asked to write the conjugate acid for each of these bases shown here, how would you do that, right? So using that as a guideline, see if you can come up with what the conjugate acid would be for all of these base pairs, or all of these bases here, right? If we're looking for the conjugate acid, that means that these would all be bases. Be the conjugate acid for HS minus. What does a base do in terms of Bronsted-Lowry acid and base? It accepts a proton, right? So if this is the base and we want to find its conjugate acid, that means we need to accept a proton to become a conjugate acid, right? So H becomes what? What do you guys think? If it accepts a proton, what will be the chemical formula then? H2S, right? So HS becomes H2S. This would be the conjugate acid. Right here we actually have a weak base, ammonia, NH3. What will NH3 become? NH4, right? NH4, and then NH4 would be a positive charge here, right? NH4, ammonium, is a positively charged polyatomic ion. And what about our carbonate ion, or our bicarbonate ion? This will become HCO3 minus. Each proton carries a positive charge, right? It is just a single proton, it carries a positive charge. So we just add a proton to that formula and we get rid of one of the negative charges, right? The proton cancels out one of the negative charges. All we're doing for acids and bases is moving protons, right? We're not changing the oxygens, we're not changing the number of carbons. We're just changing the number of protons. This can also act as a base again and accept another proton, right? So this is what we call a polyprotic acid or a polyprotic base. This would be actually I'll protonate it again because it can actually accept another proton to become H2CO3. This is a carbonic acid molecule. And this is called a polyprotic acid because it has multiple protons that it can dissociate. And so that's how we identify. Vanessa? So these are always coming from water. How we describe acids and bases is what happens when we put these compounds in water. So for all of these, HS minus reacts with water. It accepts a proton from water, and bases should create what in solution? All right, from our Arrhenius definition, what should bases do in solution? Yeah, they should create hydroxide, OH minus. So the base accepts a proton from water to then create H2S, which is our conjugate acid, plus a hydroxide ion. So that's where we're always accepting the proton or donating the proton to, is we're reacting with water somehow to either make H3O plus if it's an acid or make OH minus if it's a base. So we're looking at the movement of this proton. So we're not writing out the full chemical equation here, we're just looking what is the actual conjugate acid for the base. How does it act once we put it in an aqueous solution? Good question. All right, does that make sense to everyone? All right, so what about the reverse here, right? What should the general formula if we have an acid, right? We react with water in aqueous solution, H2O, liquid, goes to then make a conjugate base, and an acid should always make what in solution? Hydronium, right? H3O plus. All right, so using this, see if you can figure out what are the weak acid and weak base, or the conjugate bases, right? You're looking for the conjugate base for each of these weak acids. The conjugate base of HIB. Right. Let's say we have HI plus H2O, right? We need to generate what in solution for it to be an acid? H3O plus, right, or hydronium, H3O plus. And the acid does what? Does it donate or accept a proton? It donates a proton, right? So this proton is going to leave, and what should be left over after you donate the proton? I, and then we lost a proton, so it'll be I minus, right? Whenever we're talking about dissociation of hydronium or a proton in this case, it's just the proton. It doesn't carry the electron with it. This is what makes acids and bases so reactive, is that a single proton is a very reactive species. Right, so this will be, the conjugate base will be I minus. Below that you have methanol. What would the conjugate base of methanol be? And so this one might be a little confusing when we first look at it. But generally, whenever you see an acid or a base written, you see there's two protons, two sets of protons. There's CH3OH, right? The H's are separated. The H that's alone is usually what we call the acidic proton, right? So this is the acidic proton, which means that that's the proton that we dissociate, right? That's the proton we dissociate. And when I say dissociate, I just mean that's the proton that we donate to water, that we get rid of in this case, right? So this becomes what? What do you guys think? We keep all of those protons, right, because those are bonded to the carbon atom. We lose the acidic proton, and because the proton carries a positive charge, we get C3O minus. What about the last one? It's going to be nitric acid. We only have one proton here. That's going to be our acidic proton. What should the conjugate base for nitric acid be? NO3 minus, right? Because we lost the positive charge from the proton, what's left over is a polyatomic ion. That's our nitrate ion, if you guys remember. And so we notice that acids are either positively charged or neutral. Generally, that's the case. And bases, or the conjugate bases of those acids, are going to be negatively charged. It's something to keep in mind because we're getting rid of just the proton, not the electron that comes with a hydrogen atom. All right, any questions on conjugate acids or conjugate bases for either weak acids or weak bases? No questions? All right, so there's going to be one last definition. It doesn't really change anything for our intents and purposes. These are for, so I forgot to make a slide for this, are going to be Lewis acids / bases, and I mentioned these briefly at the end of last lecture. And a Lewis acid, instead of looking at the movement of protons and what's a proton donor and a proton acceptor, we look at lone pair electrons, right? So either lone pair donors or acceptors. In these ones, it's important to understand the Lewis structure of these compounds because if you have a lone pair, it shows up on the Lewis structure. And that determines whether it's going to act like a Lewis acid or a Lewis base. And so Lewis acid is going to be a lone pair acceptor, and a Lewis base is going to be a lone pair donor. And so a lot of times you're thinking in the Bronsted-Lowry context, that's the easiest way to think of acids and bases. And if it's a Bronsted-Lowry acid or base, it's going to be a Lewis acid or base. However, there are things that are classified as Lewis acids that wouldn't be considered a Lewis or a Bronsted-Lowry acid and base, right? So it goes one direction but not the other. And so what this does is it expands the definition of an acid, and it expands it to electron deficient compounds and highly charged metal ions. And those are usually going to be D block metals. And so the electron deficient compounds, this would be something like boron trifluoride, right? These are things that I didn't ask you guys to understand the Lewis structure for them because they're okay with having a octet rule exception, right? So those things can now be classified as Lewis acids. And highly charged metal ions, something like aluminum 3+, for example, can act like an acid by this definition, right? If this is very highly charged, it can coordinate with different lone pair donating molecules. But if we were to look at something for a base, like a Lewis base, we know ammonia, right? We said this was a Bronsted-Lowry acid and base, and we know that it generates hydroxide in solution, so it's an Arrhenius base as well. In the Lewis definition, it's still considered a base because if we were to look at the Lewis structure for this molecule and understand the shape, we see that the central nitrogen has a lone pair on top of it. That lone pair can be used to basically accept a proton, right? That lone pair is used to accept a proton. That's why, the definition of a proton acceptor or Lewis lone pair donor go hand in hand with each other, right? It's just a different way of saying the same thing. The lone pair is what allows it to accept a proton in these circumstances. So really, a Lewis acid or base just expands the definition of an acid, really. Anything that's a Bronsted-Lowry acid or base or Arrhenius base will still be considered a Lewis base. It's really the acids that expanded. Yeah.
So how do you differentiate them? Like, how can you tell which ones?
They're all the same thing, right? So if you're a Lewis base, you're also a Bronsted-Lowry base, and you're also an Arrhenius base, right? They aren't distinct from each other, just how we define them is differently, right? They're saying basically as time went on, originally they said, oh, if you make hydroxide in solution, that's what defines a base. And as time goes on, they say, well, it's not as simple as that. Really, if you're a proton acceptor, that's really what defines a base, right? Because that's actually the mechanism by what we create a basic solution. And then they go along further and they say, well, a Lewis base, lone pair donor is still a proton acceptor, but a Lewis acid, a lone pair acceptor, right? That expands it because if you put aluminum, highly charged aluminum in water, or you put boron trifluoride, that'll also make H3O plus in solution. It's a more complicated mechanism, but those can also change the pH of the solution, right? So it's not that usually if you're a Lewis acid, right, then you're also going to be an Arrhenius acid because you generate H3O plus in solution. But just the definition of an Arrhenius acid doesn't necessarily mean it's going to be a Lewis acid in these cases. Right, so we're not necessarily thinking them as distinct things, right? You're either or. It's usually, are you considered an acid by any of these definitions? And you will act as an acid in these cases. Yeah, so it's more of a comprehensive view of everything that you're looking at together. That's a good question. Right? But really what we're looking at, right, the Bronsted-Lowry picture is what we look at when we look at chemical reactions, right? Because when you look at our acid or base equation that we have over there on the board, we're looking at the movement of the proton. That's the easiest thing to see. We don't really draw the movement of lone pairs. And in terms of the Lewis definition, this is more of like a multiple choice type thing, right? You can't really write the conjugate. You still can have the conjugate acid-base pairs because the lone pair gets donated to something, but it's the exact same thing as writing a Bronsted-Lowry acid-base pair, right? So all of these examples here, right, these are still all the conjugate base and acid, or the weak acid conjugate base pairs, if we're looking at it from the Lewis perspective as well, right? The acid, right, can accept a lone pair because it has a proton to give that lone pair, to give the lone pair. Right, and now its conjugate base, this I minus, has an extra lone pair on it to be like a lone pair donor. All right, any other questions on that? Right, and again, these are more definitional things, right? The actual kind of meat of the work with pH and understanding acidic and basic solutions is more in the problems that we're going to look at. It isn't necessarily. It's important to understand conjugate acid-base pairs, but once you do that a couple times, it's relatively simple. The harder part, I believe, is calculating the pH of solutions. Okay, so let's talk about acid strength. To this point, I've mentioned weak acids and weak bases, and strong acids and strong bases. And so strong acids and strong bases are those that dissociate 100%. And so what that means is that if I put hydrochloric acid, which is a strong acid or base, in water, all of it gets converted to Cl minus plus H3O plus. Right, so up there, when we drew the equilibrium signs for a strong acid and a strong base, there is no equilibrium. All of it gets converted, right? It dissociates, it gets rid of its proton as soon as it's in a solution of water. And what that means is that the concentration of your strong acid is equal to the concentration of H3O plus in solution, right? These brackets right here mean concentration. And the concentration of whatever your acid in solution, let's say you added 2 moles of hydrochloric acid, that's going to mean there's 2 moles of hydronium created as soon as you put it in water. Why? Because 100% of it gets converted from hydrochloric acid, HCl, to H3O plus. And the same thing can be said for bases, right? If we have sodium hydroxide, that's a strong base. We put it in water. this is going to dissociate into Na plus OH minus plus H2O liquid, right? And so the concentration of whatever sodium hydroxide you added is equal to the concentration of hydroxide in solution, right? Because they dissociate 100%. The reason it looks a little funnier for the base is because strong bases tend to be ionic compounds, which means that it's an ionic bond that just breaks to make hydroxide in solution. Whereas hydronium, when that's created, it's because the hydrochloric acid still donates a proton to the water molecule. And so these are the same thing as a strong electrolyte. All right, so a strong electrolyte is something that dissociates completely. Does anyone know any strong electrolytes that we've talked about? If I were to ask you to give me an example of a salt, what would you say? What's table salt? Sodium chloride, right? So an example, sodium chloride, when you put it in water, right, it dissociates 100% into sodium ions and chlorine ions. And the water molecules kind of just surround it, right? That's what it means for it to be a strong electrolyte. I'm sorry, I didn't mean to draw these, right? These arrows should all be in one direction for strong acids and bases or strong electrolytes. Why? Because there is no reverse reaction. We don't remake, spontaneously, we don't remake sodium chloride from sodium ions and chlorine ions in solution. And this is important because when a question asks you, oh, if I put 2 molar sodium hydroxide in water, what's the pOH of the solution? You have to understand that the OH minus concentration is equal to the concentration of the base that you're adding in. And so for acid and base strength, right, if those are strong acids and strong bases, weak acids and bases are those that only ionize partially in water. And so that we define as a weak electrolyte. That means that if we put our acid in water, instead of the reaction only moving in one direction, we donate the proton and we create our conjugate pair, and we either generate hydronium in solution, or if we put our base, our weak base in solution of water, we generate our conjugate acid plus OH minus. And these arrows here, right, these signify an equilibrium. Right, where the reaction is moving in both forward and reverse directions. So this reaction moves in forward and reverse directions. So that means when I put HA, whatever that is, it could be acetic acid, I put acetic acid in solution, it's only going to make a little bit of acetate and a little bit of H3O+, because it doesn't dissociate completely to form all the H2O+ possible, right? So I'm going to have both HA and A- present in the solution. For the base, I wrote the base equation a little bit differently than I did here. B and A- can kind of go hand in hand with each other. Generally, when you're talking about a base, it's B. So we add that to water, it accepts a proton because it's a base, right? And it creates our conjugate acid and OH minus in solution. But this doesn't happen 100%. Not all of this gets converted into this. There's a ratio of both HB plus and B in solution. For acids, there's a ratio of HA and A minus present in the solution. And this has to do with the idea of equilibrium. Once you reach equilibrium, we'll talk about that in a second, the concentrations of everything is not changing anymore. I mean, the concentration stays the same, but reactions are still happening in the forward and reverse direction. We still have some products being made and some reactants being made from the products, but the overall change stays the same, right? So if one reaction happens forward, the one reaction happens backwards, right? So nothing has changed really. And so again, these are weak electrolytes, meaning they don't dissociate completely in solution. And so calculating the equilibrium concentrations of H0 plus in these cases is beyond the scope of what we're going to do in this class. If you go on to Chem 102, you'll do plenty of that there. You actually have to do some algebra to figure out what is the concentration of H0 plus and OH minus in solution. Right? So how would we represent that? Graphically, if we have a strong acid, right, we add that to water, and all of it, right, see the level here is the same, all of this gets converted into H0 plus and A minus, right? We donate 100% of these protons to the water to then generate H0 plus and A minus. For a weak acid, right, not all of the protons are donated to water, so we still have a lot of our weak acid present at equilibrium, and only a small fraction of H0 plus and A minus in solution, right? And that's because, and it'll be, you know, funny when you start hearing about this, but you can have strong weak acids or weak acids because the degree to which they ionize or how much H0 plus you make in solution depends on, you know, what is the equilibrium ratio for this. All right, so this is how we visualize it, right? HA, and again, for the acid here, HA, the concentration, is equal to H3O plus, H3O plus, for the strong acid, strong base scenario. And we're gonna be mostly focusing on the strong acids and strong bases for the purpose of this class. The only thing you ever look at for weak acids and weak bases is identifying the conjugate pairs. We're not gonna be looking at pHs or pOHs of these solutions. All right, so what are some common examples? So I've mentioned some, usually the halogenated or hydrogen halogens are pretty strong acids. It's very easy for them to dissociate their proton, so they're strong electrolytes, make some strong acids. Nitric acid, sulfuric acid, hydrochloric acids are the ones you see a lot. Weak acids, acetic acid, like what we did last time, that's like our, what's in vinegar, carbonic acid, phosphoric acid, hydrofluoric acid, and then some of the other ones there too. Those are all considered weak acids, right? So these, again, strong acids, we define it as what? How do we define a strong acid? Yeah, it dissociates completely. In this, dissociates only partially. And again, when we say dissociate, we just means once we put it in water, you know, how much H3O plus are we making in solution, right? How much of the protons are we dissociating from our weak acid? Okay. And I'm not going to expect you to memorize a lot of these. The ones that you'll be common to get really acquainted with are nitric acid, sulfuric, and hydrochloric acid, because those are just ones you see a lot. Generally, you make solutions from strong acids because it's easy to get the pH of those solutions. All right, what about common bases? Some strong bases, lithium hydroxide, sodium hydroxide, calcium hydroxide. You notice these are all mostly going to be ionic compounds. That's because when we put them in water, it just dissociates a hydroxide ion. So you don't even have the mechanism of accepting a proton from water. You just create OH minus from solution. And then weak bases, we have urea or ammonia. Those we consider weak because they only partially ionize. In these cases, when they ionize, they accept a proton. All right, so these, I'm going to write it a different way just so you see both ways. Ionize partially, and these ionize completely. And when these ionize completely, they do it the same way that sodium chloride does in a solution, because it's easy to make actual salt crystals out of sodium and little hydroxide ions. All right, any questions on strong acids strong bases, weak acids, weak bases. Vanessa?
What does ionized mean again?
Ionize just means it dissociates to make ions, right? So that's a good question. Ionize, this means to make ions. And ions are what? Who remembers what an ion is? The general definition. Yeah, a charged molecule or atom, right? Charged molecule or atom, right? So when ammonia ionizes, it becomes ammonium, NH4 plus, right? That's a charged molecule or atom. If we look at hydrochloric acid, right? When we put this in solution, it becomes Cl minus and H3O plus, right? When it interacts with water. So it's created two ions. So that's why we say ionize, dissociate. They are all used interchangeably with acids and bases. A lot of times when you go farther in chemistry, people think of acids and bases as distinctly different from understanding ion formation, but really you're just looking at the concentrations of very specific ions with acids and bases. And what are those ions? H3O plus and OH minus, right? Instead of looking at sodium and chloride, sodium ions or chloride ions, we're just looking at OH minus and H3O plus. That's what we're focusing on with acids and bases. And why? Well, because there's so much aqueous solutions around us and inside of us, it's very important for most processes that happen in water. Good question. I'm glad I got to clear that up. All right. So what is equilibrium, right? So equilibrium is a representation of the concentration of reactions. So it's going to, of the concentration of products over the concentration of reactants, right? These brackets here mean concentration, reactants, and they're usually raised to the coefficient, so M and N. These would be their stoichiometric coefficients. So we're only going to be talking about equilibrium in the context of acids and bases, which makes it really nice because acids and bases, when we looked at neutralization, when we were doing our titrations, our neutralization reaction always had a stoichiometric coefficient of what? Who remembers? For everything. All right, so our neutralization was something like sodium hydroxide plus hydrochloric acid. That formed, what do we always form in a neutralization reaction? Water. And then we had salt, sodium plus chlorine, right? For our neutralization reaction, is this a balanced equation? How many oxygens are on the reactant side? One. And how many are on the product side? One. How many sodiums are on the reactant side? One. And how many are on the product side? It doesn't have to be neutral, right? It doesn't have to be neutral. It can be positive. So how many are on the product side? One, right? And how many chlorines are on the reactant side? One. And how many are on the product side? And what about hydrogens? How many hydrogens are on the reactant side? Two. And how many are on the product side? Two. So is the reaction balanced? Yeah, it's balanced. So the nice thing about neutralization reactions and acids and base reactions in general is that everything is always in a 1-to-1 ratio, right? So these coefficients that I wrote there and the powers for the concentration, right? These quantities right here are always equal to 1, which makes things a lot simpler for us. And usually, it's the product of the concentrations raised to their coefficients, right? So if we only have one reactant, one product, then it's just what we wrote here. But if there's multiple, each concentration is multiplied by each other, right? And so this ratio, what it does is it represents the concentration of the species in the chemical reaction at equilibrium. Right, so what that means is how much products and how much reactants do we have in our solution, and what's the ratio of them? right? And that constant is always gonna stay the same for that reaction. Unless you change the temperature, that constant, that ratio is always gonna be the same. You can have actual different amounts in solution, but the ratio has to stay the same. That's how we define equilibrium, right? So for example, if I had 2 products and 1 reactant, then I would have 2/1. That gives me a ratio of 2. That's the equilibrium constant for that reaction. But what if I added 6 products and 3 reactants, right? I have more of each of them, but the ratio of them is still equal to 2. That's going to be the new equilibrium concentrations, but the ratio itself has to stay the same. And what equilibrium means is that if, let's say you put something else that wasn't a ratio of 2 in there, let's say I put 9 and 3, the concentrations, the reaction will move until it reaches that ratio again. And then the reaction is still happening, but at that point it's happening such that if one reaction happens forward, one reaction happens backwards. So there's no change in the concentrations anymore, right? And so equilibrium is when the reaction is still happening in the forward and reverse directions, if it can, but the concentrations remain constant. And in future chemistry courses, you'll go into how this is related to thermodynamics and energies and things like that. But right now, this is something that was developed independently just by understanding, well, nature always has to move towards something, right? And what is it moving towards? Nature's always moving towards equilibrium. And this isn't just an idea in chemistry, this is an idea in physics, biology, all of these things deal with equilibrium. And so it puts a numerical value to the ratio of the concentrations of the reactants and products. And this ratio is basically a property of the reaction, right? This is a property of the reaction. And just to be thorough, I'm going to put at a given temperature, right? If you change the temperature, that's the only thing that'll really change the temperature or activation energy, that'll change the concentration of the reactants and products at equilibrium. So that means whenever I have a neutralization reaction of sodium hydroxide and hydrochloric acid, that it has a associated equilibrium value with that reaction. So no matter how much of each of those reactants and water I add to the system, it's always going to move the reaction until it reaches this ratio again. And so the idea of equilibrium is a pretty deep idea. It required a lot of thought to kind of come up with. And it's something you guys will become familiar with. Not as much in this course, but in future courses. But it's important for acid and base chemistry because for weak acids and weak bases, this equilibrium, right, is how we determine how acidic or basic a solution is. Are any questions on equilibrium? Kai? It's in every single chemical equation. So when we talked about our redox, right, there's an equilibrium constant associated with the redox reaction, right? What is the ratio of products and reactants going to be, right? If I put in random amounts, the reaction will move until it reaches that ratio. And everything, no matter what that reaction you're looking at, is going to move until it reaches that ratio. Sometimes those ratios are really large, which effectively means, like for strong acids and strong bases, that ratio is almost like infinity because it dissociates 100%. You're going to always have only products and the reactants is going to be very small. But other reactions, like a redox reaction, for example, that one, they could be very similar to each other. Maybe it's a 50-50 ratio. So the reaction will always move. Let's say I add 90% products and 10% reactants to a mixture. It'll move until you have 50-50 concentration or equal concentration of both. Yeah, good question. This is something ubiquitous in all of chemistry and in physics too. So for example, if you take a physics class and you're looking at the balances of forces, when forces balance out, that's when you have an equilibrium of forces as well. Right? A ball starts at the top of a hill, it rolls down to the bottom of the hill, right? It's moving until it reaches equilibrium, where everything is balanced and there's no movement anymore. This is the same idea. everything is balanced, there's no movement of the reaction anymore. It's still happening, but the concentrations, there's no movement of the concentrations anymore. Good question. All right, so how does this relate then to acids and bases explicitly? Well, we know that water can act as both an acid and a base, right? We talked about that last time. What did we say that meant water was called? Does anyone remember the name? Kind of sounded like amphibian a little bit, right? Something that can be on land and water. It was an amphoteric material, right? Amphoteric material, right? It can act as both an acid and a base, which means it can do what with protons? It can both donate and accept protons, right? So that means that if you have a neutral solution of water, right? We think of water as being neutral because we drink it, right? It doesn't harm us in any way. Two water molecules can come together, and one can donate a proton and the other one can accept a proton, right? And if one donates and one accepts, what two ions do we create? What do you guys think? What happens to water after we donate a proton? What's left over if we get rid of a hydrogen? Yeah, you can say that becomes oxidized in a way. And what's the ion that's left over? Okay, hydroxide, right? So we get one becomes OH minus, and what happens to the other water molecule? What does it become? It gains a proton. It gains becomes H2O plus, hydronium, right? So this means that this can happen in neutral water. And if we were to write the equilibrium for this reaction, right, the equilibrium constant, the thing about equilibrium constants is the only states of matter that you include are aqueous compounds and gases, right? Those are the only two things that you include. And we're not going to go into the details or the theory of why that's the case, but I'm just going to assert that to you. We only include aqueous species. So the products here are OH minus and H0 plus. So the equilibrium constant for what we call the auto ionization of water, right? It means this automatically happens because it can act as both an acid or a base. It automatically ionizes to some extent in just neutral water, right? It's called Kw, is our equilibrium constant. That's the ratio of products to reactants, the concentration in this case. We don't include liquid molecules, so the water doesn't show up. So all we have is this is equal to the concentration of OH minus and the concentration times the concentration of H3O plus. Right, so that value that I put, that ratio that I put on the previous slide, this is the exact same thing for this specific reaction, right? This is our equilibrium constant. And so you can measure this in neutral water to see, well, how much OH minus and OH plus is present in neutral water. And if you guys had to guess, if the water is neutral, how much OH minus and H2O plus do you think there is relative to each other? Meaning, if you were to compare these two, how do you think they'll be in neutral water? Something kind of like zero, right? They should cancel out somehow, right? H2O plus carries a positive charge, and OH minus carries a negative charge, right? So if you have equal amounts of both, they'll cancel each other out. So we say, well, in a neutral solution, then H3O plus has to equal OH minus. In a neutral solution. And so this is what's actually gonna define us the concentration of either hydroxide or hydronium in neutral solutions. This idea will, we know this happens in water automatically, right? It automatically ionizes, and there's some equilibrium value that's associated with that. So if we can measure what that value is, then that'll tell us what the concentration has to be in a neutral solution. And so if you were to measure this value, Kw is equal to 1.0 times 10 to the minus 14. And so if you guys are sick of units, well, this is your lucky day, because equilibrium constants don't have any meaningful units, right? So we don't have to write any units for equilibrium constants. We do have to be aware of what it is that we're calculating, but we don't have any units for an equilibrium constant. So this is a value that people measure, scientists measure experimentally, right? And this is at room temperature. So scientists measure this value. And using these two together, what we get is that, am I good to go on to the next slide, or is anyone still writing? Should make sure. Good. And so because we've measured this value, and we know this has to be true in a neutral solution, we can then solve this for what is the concentration of H3O plus in a neutral solution. Okay, so that means we have 1.0 times 10 to the minus 14 equals H3O plus, and then OH minus in a neutral solution equals H3O plus. So we replace OH minus with H3O plus. Right? If those two things are equal in a neutral solution, I can replace this OH minus with an H3O plus. That's right, I just replaced, those two things have to be equal to each other, so I just replaced one variable with something that's equal to it. This is like the same thing as writing H3O plus squared, right? And if I want to solve for what H3O plus is, or isolate it, how do I do that in this equation? All right, so I have simplified 1.0 times 10 to the minus 14 equals H3O plus squared. How do I isolate H3O plus? How do I get rid of that square sign? Yep, take the square root of both sides, which is the same thing as just raising both sides to the half power, right? That's the same thing as a square root. Whatever you do to one side, you have to do to the other. And using laws of exponent, we don't even have to plug this into our calculator, right? The square root of 1 is what? 1 squared is equal to what? 1, right? So 1 times 1 means the root of 1 squared is just 1, or plus minus 1 technically. So this becomes 1 times 10 to the minus 14 divided by 2 is equal to, and then these two will cancel out with each other, right? Because we multiply exponents together. So this gives me H3O plus. 14 divided by 2 is equal to what? 7 minus 7, which means that for a neutral solution, the concentration of H0 plus has to equal 1 times 10 to the minus 7. Okay. Does anyone remember from maybe a previous class or just real life experiences what the pH of a neutral solution is? 7, right? So we see now, okay, well this is probably where the pH is going to come from somewhere here, right? Because this is saying this exponent is to the power of 7. So maybe these two are going to end up being related. The exponent of the concentration of H3O plus is going to tell us about the pH of the solution. And so the pH is similar to the Richter scale for earthquakes, right? It's not a linear scale, it's a power scale, right? So it's going to tell us about the order of magnitude of the concentration of hydronium in solution. The more hydronium we have, the more acidic the solution will be. the less hydronium we have, the more basic the solution will be. Right? So this is where the shifting scale is coming from. And so that means that all solutions are going to have some amount of H3O plus. And if you change that amount of H3O plus, equilibrium says that you're going to have to adjust OH minus in the solution such that it always equals the equilibrium constant, the ratio that I showed you guys on the previous page, right? No matter what, if I increase this H3O plus, then this is going to have to go down to keep this number the same. Why? Because we're always moving towards this ratio. This ratio defines how much OH minus and H3O plus, what the relative amount should be in solution, no matter what, because that's a property of this ionization reaction. If we add one or remove one, you have to adjust the other to compensate so the ratio stays the same. So this is what I just said. When the concentrations of H3O plus and OH minus are multiplied together, right, that gives us Kw. Right, Kw is always equal to H3O plus and OH minus, the product of these two. Right, so if I increase H3O plus, then to keep this the same, right, I increase this value, OH minus has to go down so that the product of the two stays the same, right? Let's say, you know, for example, our equilibrium constant is 1.0 times 10 to the minus 14 here. But if I had an equilibrium constant of 2, right, and initially I had 2 H0 plus and 1 OH minus, that ratio stays the same. But let's say I increase H0 plus to 4 in that case. To get the ratio to be 2, OH minus is going to have to go from 1 to 0.5. Why? Because 0.5 times 4 still equals 2. This number always has to stay the same whenever we're looking at equilibrium. And so then if we decrease H3O plus, you just have the opposite happen. Kw equals H3O plus. So we decrease this amount, then the amount of OH minus in solution has to go up to compensate to keep this number the same. This equilibrium ratio or constant has to stay the same. Okay, am I good to go on? And when H3O plus is greater than the OH minus in the solution, we define that as acidic. So if we have a concentration of H3O plus that is 1.0 times 10 to the minus 4 molar, then the concentration of OH minus has to be such that when you multiply them together, they are equal to what? Right, our relationship is that Kw is equal to H3O plus times OH minus. Which means that if you're given the H3O plus value, this value is always the same. So this is going to be 1.0 times 10 to the minus 14 is equal to 1.0 times 10 to the minus 4 is equal to OH minus. So you can always solve for the concentration of one if you're given the concentration of the other. Which means that if you were to divide both sides by, this is molarity, 1.0 times 10 to the minus 4, 1.0 times 10 to the minus 4, this cancels out there. This will give us that OH minus is equal to 1.0 times 10 to the minus 10 molarity. Again, the equilibrium constant doesn't have units, but we know it has to be in units of molarity because we're talking about a concentration of OH minus. All right, so this would be 1.0 times 10 to the minus 10 molarity. And we see that we have 10 to the minus 4 is more, or is larger or smaller than 10 to the minus 7. What do you guys think? Okay. Yeah, is 10 to the minus 4. If we look at these two numbers, 10 to the minus 4 and 10 to the minus 7, which one is larger? Yeah, because it's a a smaller negative number, right? So this is like 0.0001, and this is like 0.000001, right? The number on the left is larger. They're both small numbers, but the number on the left is larger, right? Which means that to make sure that the H3O plus concentration, since it got larger, OH minus concentration had to do what? It had to get smaller such that it equals this ratio right here, right? So whatever happens to one, the opposite happens to the other. And this is going to give us basically the two different ways that we can always look at acidic or basic solutions. You can always look at it from the perspective of hydronium or hydroxide. Why? Because their product always has to be equal to the equilibrium constant. Right, so if we have the OH minus concentration is larger than H3O plus, that's how we define a basic solution. Right, so if the concentration of OH minus is 1.0 times 10 to the minus 6, then see if you can find out what the concentration of H3O plus would be. And again, you're always starting from Kw equals H3O plus times the concentration of OH minus. Why? Because that product always has to be equal to Kw, which was 1.0 times 10 to the minus 14. All right, so what did you guys get for your concentration for H3O plus? Right, so initially this is 1.0 times 10 to the minus 6 molar. Divide that to both sides. 1.0 times 10 to the minus 6 molar. Cancels out on this side. Then H3O plus is equal to 1.0 times 10 to the minus 8 molar solution. I did this without using a calculator just because I can use the rules of subtracting exponents, right? Negative 14 minus negative 6 is like negative 14 plus 6, which gives me negative 8. This would be 1.0 times 10 to the minus 8 molar. And so in this case, for a basic solution, we see that the concentration of OH minus is larger than 10 to the minus 7, which it would be at a neutral solution. And so to compensate, right, OH minus went up, what had to happen to H3O plus?
I'm sorry, say that again.
OH minus, right, this concentration went up. What had to happen to H3O plus? This had to go down, right? And if we look at the values, 10 to the minus 8 is smaller than 10 to the minus 6, right? That's because they always have to multiply to equal our equilibrium ratio, right? This is a property of the system. These two things together always have to equal the equilibrium constant. All right, any questions on the algebra or the ideas behind this right now? So the last thing I'm going to introduce is the pH scale. It'll only take a second. Okay, so the last thing we're going to look at is the pH scale. And the pH scale is going to give us a relative order of magnitude for how acidic or basic a solution is. So the pH scale, does anyone know the range for the pH scale? Yeah, it's like 0 or 1 to 14 usually. 1 to 14 is usually the range for the pH scale. Acidic solutions are less than 7, so low pHs, and basic solutions are greater than 7. So how the pH scale works is the pH is defined as the minus the logarithm, right? Remember, logarithm was one of those mathematical operations we talked about earlier in the semester, of the concentration of H3O plus. Right? We have this negative sign because concentrations are small. The logarithm, what this does is it tells us the size of the exponent. Right? So if we have, this tells us the size of the exponent. So if we have something like 10 to the minus 8, right, minus the logarithm of that is equal to 8. Right, so the logarithm tells us a relative order of magnitude. If we can put it on a scale, how large is the exponent for this value that we're looking at? So because the concentrations of H3O plus are very, very small, we use a logarithm to say, well, you know, a pH 7 is a neutral solution because that's where the concentration of a neutral solution of H3O plus has to be, right? It was 1.0 times 10 to the minus 7. That's how we define that pH 7 is a neutral solution. As that concentration gets larger, minus the logarithm of that number gets closer to 1. As that concentration gets smaller, minus the logarithm of that number gets closer to 14. And 14 was the size of the exponent of our equilibrium constant because we're saying the maximum we can exist is between those values because we have to equal 10 to the minus 14. All right, so this is where the pH scale comes from. And from this, you can then get the pOH scale and a relationship between those as well. So we'll end there for today. And then we have a lab going over production of oxygen gas. So we'll finish up probably a little bit of acids and bases up there. And then on Wednesday, we'll talk about gases and ideal gas laws. All right, so I'll see you guys.